Today we will continue our class on unsteady state heat transfer. In this class I will explain the usage of Heisler's chart for an infinite cylinder. As I mentioned in the previous class, while using Heisler's chart, the characteristic length for an infinite cylinder is taken as R0, where R0 is the outer radius of the cylinder. So it is infinitely long, so that conduction takes place only in the radial direction. There is no conduction along the length of the cylinder. So there is no conduction taking place along the length. The conduction is happening only in one direction, that is along the radial direction. Since it is too long, the heat cannot flow in this direction. So heat will flow only towards the surface, where it will have least resistance to heat flow, because this distance is small compared to the other end surface. So this is offering a lot of resistance to heat flow. So when it is an infinite cylinder or very long cylinder, the conduction will be in one direction. And it is an unsteady state process. The temperature is varying with respect to time also. So when it changes with respect to time, and also changes with respect to distance, but only in the radial direction. So initially, given the axis and surface all everywhere, at any radius you take will be at initial temperature, which is Ti. But later on, a surface will cool fast, whereas axis temperature will remain at a higher level. So it will be at higher temperature. Axis will be at a higher temperature, whereas surface cools fast. So there will be a difference in temperature between axis and surface. So there will be a variation in temperature from axis to surface. So with respect to the radius, we can find out the temperature. So for that you need to use the Heisler's chart. There are three charts. The first chart is used to find out the axis temperature. From the chart you will get the temperature difference. Theta naught by theta I we will get. So from that you can calculate theta naught. Theta naught will give the center temperature difference at the end of a specified time period. So center temperature difference if you get, you can find out the center temperature. So next second chart will give theta by theta naught. Theta at what point you require. Suppose you want at a radius r, then r by r naught, that fraction you should take, and then from the chart you can calculate the temperature difference at that particular radius. And then once you get the temperature difference at that particular radius, you can find out the temperature at that point. So using the first chart you get theta naught, using second chart you can find out the temperature at a given radius. And then another chart is there, that is to get the fraction of energy removed from the infinite cylinder. There you get the heat removed from the, or heat transfer from the body in the specified time period. So I'll explain this with an example problem. Its chart reading everything is similar to the infinite flat plate. So here charts you need to read for an infinite cylinder. And characteristic length is for the infinite cylinder is R outer radius. So we will work out an example problem. A long aluminum cylinder, 400 mm diameter, and initially at 200 degrees centigrade, is suddenly exposed to convection environment at 60 degrees centigrade, and H is 500 watts per meter square kilometer. Calculate the temperature at a radius 100 mm and the heat lost per unit length 5 minutes after the cylinder is exposed to the environment. Given K is equal to 200 watts per meter Kelvin, Cp is equal to 900 joules per kilogram Kelvin, and ρ is 2700 kilogram per meter Kelvin. So the properties are given, and the heat transfer coefficient is given, the initial temperature is given, and ambient temperature is given, diameter is given. Okay, so you need to find out the temperature at the radius of 100 mm. Radius is actually, the diameter is 400 mm, so outer radius is 200 mm, and you have to find out the at a radius of 100 mm. So it's not at the outside surface, interior point. At a radius of 100 mm, you have to find out the temperature. And heat lost per unit length, that is per unit length. So it is infinitely long cylinder. So at 1 unit length, what is the heat lost at the end of 5 minutes? Heat lost per unit length 5 minutes after the cylinder is exposed. So starting of the cooling process, 5 minutes later, what is the heat loss per unit length that you have to calculate? So let us solve this. Characteristic length is outside radius, which is diameter by 2. Okay, that is radius is diameter by 2. And diameter is 400 mm, so you get 200 mm, that is 0.2 meter. By number is HL by K is a formula. The characteristic length in this case, while using the Heisler's chart, is R0. So H R naught by K, and H is heat transfer coefficient 500 watts per meter square Kelvin. R naught being 0.2 meter, and thermal conductivity of material is 200. So you get the white number as 0.5. And reading the chart, we require 1 by white number. So we will calculate that 1 by 0.5 as 2. 1 by white number, inverse reciprocal of white number is 2. And alpha is a thermal diffusivity, is K by rho Cp, thermal conductivity is 200, density 2700, and Cp is 900 joules per kilogram Kelvin. So substitute that, you get thermal diffusivity as 8.23 into 10 raised to minus 5. This thermal diffusivity is meter square per second. So much meter square per second it has to be specified. And Fourier number is alpha t by L square, alpha t by R naught square, because the characteristic length is R naught in this case. So substitute that values, you get Fourier number as 0.617. These are the two quantities which you have to pick, 1 by white number and Fourier number. So this chart axis temperature for a long cylinder as a ratio of the initial temperature difference. So it's the center temperature difference divided by initial temperature difference theta I. That ratio you are getting from this. So you require Fourier number and 1 by white number. So Fourier number is 0.617 and 1 by white number is 2. 0.617. 0.617 it will come here. This area will go for this. Here it is 0.2, 0.4, 0.6, 0.8 and 1. So here 0.617 will come somewhere here. And corresponding to 1 by white number 2, you can follow that reach here. This is the point where it meets the 1 by white number, that is 2. 2 is a straight line, meets here, and from there you can draw a horizontal which gives value 0.7. So that is the value of theta naught by theta I. So theta naught by theta I you are reading from the chart as 0.7. So from Heisler's chart, for axis temperature for an infinite cylinder, we get theta naught by theta I is 0.7. Now theta naught is 0.7 into theta I. Theta I we know initial temperature difference. Initial temperature is 200 and ambient temperature is 460. So initial temperature difference is 140 into 0.7, which will give 98 degrees centigrade. So this is the central line temperature difference at the end of this time period. That is, what was the time given? Time was 5 minutes. No? At the end of 5 minutes, we have a axis temperature difference of 98 degrees centigrade. After 5 minutes, initially it was, what was the temperature difference? Initially it was 140 degrees centigrade. Even axis was at 140, surface was at 140. At the end of 5 minutes, that is 300 seconds. The temperature difference at the axis is 98. Now you have to find out the temperature at the axis. Theta plus temperature, this is theta 0 plus TA. So whatever temperature difference, theta 0 plus TA, which will give 98 plus 60. So that is 158 degrees centigrade. So you get the temperature at the axis at the end of 5 minutes as 158 degrees centigrade. So this is axis temperature at the end of 5 minutes. Okay. Now at the end of 5 minutes, you have to find out the temperature at the radius 100 mm. So for that you need to find out the position. R is the radius at which temperature is required. So R by R naught you need to find out. This fraction you should find out. R is 100 mm means 0.1 meter and R naught is 200 mm, that is 0.2 meter. So the ratio will get as 0.5. So this is required to read the next chart, R by R naught. Let's use correction for temperature. Position correction for temperature for an infinite cylinder. So 1 by white number you know, it is white number was 0.5, 1 by white number was 2, it is 2. So this is 2, 3, 5, 6, like it's going. Okay. So 2 is there, exactly 2 is here. So 2 you can, from 2, what is the value of R by R naught? 0.5. So 0.5 is between 0.4, this is 0.4 here, curve is 0.6. And between this, center of this, that is 0.5. 0.5 will move like this. Okay. So produce that to 0.5, that is the center of this, and the gap is somewhere, the center of that. And from there, you just draw a horizontal to make this. So that will give the 0.9 and this is 1. So you give approximately 0.93. 95 is here, 93, 0.93. So that is theta by theta naught. Where theta is the temperature difference at that radius divided by axis temperature difference. Axis temperature, theta naught is axis temperature difference. Theta is the temperature difference at that radius. Heisler chart for temperature correction, theta by theta naught is 0.93. So theta is 0.93 times theta naught. So 0.93 into theta naught we got earlier as 98 degrees centigrade. That is the center temperature difference. So you get theta as 91.14 degrees centigrade. So you can find out temperature as by adding the ambient temperature. So 91.14 is the temperature difference plus ambient temperature which is 60. You get 151.14 degrees centigrade as the temperature at a radius 100 mm at the end of 5 minutes. Whereas the center line temperature was 158 degrees centigrade. Now axis is at a temperature of 158 degrees centigrade at the end of 5 minutes. Whereas at a radius 100 mm it is 151.14. This is at a radius 100 mm. So suppose you need to find out the surface temperature, then position ratio R by R naught will be 1, because we require at a position where R is equal to R naught, that is at the surface. This is at a radius 100 mm. Radius is 200. At a radius of 100 mm, somewhere in this position, we calculated the temperature. Suppose you require at the surface, then our radius is R naught itself. So R by R naught will be 1. In that case, this is a line 1, and corresponding to that 1 by number 2, we will get this point meeting this 1. So here you will get 0.7. This is 0.7, 0.78. So 0.78 as theta by theta naught. So we can find out the surface temperature. It is, in this case it was 0.93, the fraction was 0.93, now it has come down 0.78, and the temperature will be, temperature difference will be 0.78 by multiplied by 98. Correspondingly you can calculate the temperature difference and then add ambient temperature, which will give the surface temperature. And you can observe that surface temperature is going to be less than these temperatures. So axis will be hot, and as you move on to the surface, temperature will decrease, because convection is not happening at a faster rate. Temperature is not attaining uniformity within the body. There is a variation of temperature from the axis to the surface. That's why we cannot use lump heat analysis. There is a lot of variation of temperature, and convection is taking place inside the material. Temperature variation with respect to position we cannot neglect. So we have gone for one-dimensional and steady state analysis, and Heisler chart will give the solution in a graphical form. Next, you need to find out the energy removed or heat transfer from the body in the first 5 minutes. So for that, another parameter we will calculate is white number square into Fourier number. White number is 0.5, 0.5 square into Fourier number is 0.617. So if you substitute, you will get 0.154 as the white number square into Fourier number. Now we'll move on to the next chart. White number square into Fourier number. Here it is 0.1. This is 0.01. This is 0.1. This is 1. And stand like that. So this is 0.1. This line is 0.1, and this is 0.2. This line is 0.2. We require 0.157. 157. So that is somewhere in between this 0.1 and 0.2. And I've drawn a line here to meet the white number, constant white number line here. 0.5 is the white number. So I have produced this from here 0.157, approximately 0.157. From there I drawn a vertical to meet this constant white number line 0.5. From there you can produce here and get the fraction of energy removed. You get 0.38. Okay. Approximately you can read it as 0.38. That is Q by QA is 0.38. So it's a semi-log plot on the x-axis is semi-log. We will have multiples of 10. Say like this is 10 raised to minus 1. It will be 1, again 10, 100, 1000, etc. In between you will have, if it is 0.1, 0.2, 0.3, 0.4, etc. 1. Then after this the gap will be 1, 2, 3, 4, 5, etc. Here the gap is going to be 10, 10, 20, 30, 40, etc. Here the gap will be 100. But it's not uniform. The gaps are not uniform. 100, 200, 300, etc. When it comes to that, it will become very close in some lines and very merge with this. Okay. Now we got the Q by QI is 0.38, 0.38, okay, 0.38, and Q is equal to 0.38 into QI. QI is the initial energy content of the body that you can calculate using mCp into temperature difference. So M is OV Cp into Ti minus Ti. So 0.38 into rho volume is pi r naught square outer radius. So this is cross section and area multiplied by length pi r naught square into L into Cp into Ti minus Ti. So L we have to calculate for unit length. So I will substitute that as 1. So L is 1 and density is known 2700. R naught is 200 mm radius, so 0.2 meter. And the initial temperature, ambient temperature, Cp value 900 joules per kilogram Kelvin. So all that we can substitute. So what you are getting is for unit length from 1 meter length, how much heat is lost in the first 5 minutes. This is for 5 minutes. What we are calculating is for 5 minutes. So in 1 meter length, how much heat energy is removed from the cylinder to the surrounding. So the fraction we got based on the initial energy content, we got the fraction as 0.38. So 38% of the total energy content is removed. So 38% of that is 16 point. You get it's 16 into 10 raised to 6, 16.25 to 245 to 10 raised to 6 joule. So it can be converted into megajoule by dividing by 10 raised to 6, 16.245 megajoule. So much of energy is removed in the 5 minutes time duration from a very meter length of the cylinder.